Hi, my name is Ganesh and I'm a fourth-year PhD student at the National University of Singapore, and I'm glad to share our work with the SfN community. Still and Morris showed that when target platforms in the water maze were shifted every 4 trials, rats were able to learn the new location in the subsequent trials. However, the speed at which they were able to navigate to the new targets became faster as the number of sessions progressed, eventually showing a one-shot learning behavior where the latency for the second trial was significantly lower compared to the first. Tse and colleagues expanded this into a multiple pet association task where rats had to navigate to a target sandwell based on the order cue given. Rats took about 10 days to learn 6 combinations of flavor location mapping and spend more time at the target sandwells during the non-rewarded probe trials. After this training, 2 out of the 6 flavor location combinations were replaced and the rats were exposed to them for a single trial. During the probe trial, the rats spent a higher amount of time at the new targets, showing one-shot learning of the 2 new pet associates. The current hypothesis is that the rats learned the flavor location rule, and when they came across a new pair, they used a pre-learned associative rule to solve for the new pairs. However, there have been no biologically plausible models that can replicate this one-shot learning of new pet associations, and this is what our work seeks to address. We model the environment as a reinforcement learning paradigm where the agent is given a cue and has to move to the correct target location. For the single target displacement task, the target is randomly chosen in the square maze. For the multiple pet association task, the agent is initially trained on 6 original pet associations over 20 sessions. And thereafter, the agent's one-shot learning performance is assessed by introducing them to either 2 or 6 novel pet associations for a single trial followed by a non-rewarded probe trial. We studied 3 types of agents, the Monte Carlo actor critic with a single nonlinear hidden layer and trained by backpropagation. A symbolic agent based on Foster and colleagues' formulation of an agent, and an agent that has a reservoir that learns to store and recall target coordinates. Foster and colleagues developed the coordinate learning system where an agent gradually learns to estimate its XY position coordinates through date reckoning. And this is formulated by the temporal difference error. Once the agent reaches a target, the position coordinate is stored in memory as the goal coordinate. In the next trial, the agent performs vector subtraction between the target and the current coordinate to choose an action that is the shortest path to the target. With this, Foster was able to replicate Steele and Morris's one-shot learning result for single displaced targets. While the position estimation is biologically plausible, the memory system and vector subtraction modules were not. And more importantly, Foster's symbolic memory can only store single targets in its memory. And so we need to develop a biologically plausible memory system that can store and recall multiple targets. To replace the symbolic vector subtraction module, we pre-train a 2-layered neural network by backpropagation and fix the weights. We can initialize the symbolic memory using a 2D memory matrix that stores cue and goal coordinate information. When the agent is queried with a cue, we use a distance measure to recall the goal coordinate associated with the cue. Likewise, we can store and recall cue-associated goal coordinates by training a reservoir with 2 readout units. The reservoir's readout units are updated using a modified perceptron rule, where the agent's position coordinates are the target coordinates to be learned. This update is gated by the presence of a reward and can be performed within a single trial. The reservoir's weights can also be updated using a sparse exploratory Hebbian rule as well. When the agent is queried with the same cue in the next trial, the target coordinate can be recalled, showing one-shot learning. We then combine this generative reservoir model with the neural vector subtraction module to have a fully neural agent. Similar to Steele and Morris, Foster's symbolic memory agent, which is in orange, and the reservoir agent trained by perceptron rule, which is in pink, and the reservoir trained by the exploratory Hebbian rule, which is in green, show one-shot learning performance to single displaced targets. Agents took about 11 training trials to gradually learn the stable coordinate system before showing the one-shot learning performance trial 12 onwards. This was not the case for the actor critic agent, whose performance worsened over time, and this is shown in blue. The savings in latency to reach the displaced targets decreased as sessions progress. All 3 model architectures, including the actor critic, gradually learn the 6 pet associations in 20 sessions. All agents show a gradual decrease in latency and spend an increasing amount of time at the correct targets during the probe trials. When we introduced the agents to the new pet associations for a single trial, the actor-critic agent showed chance performance. Instead, our goal-directed agents were able to learn 2 and even 6 new pet associations after a single trial, and this replicates SfN21 one-shot learning performance. We increased the number of novel pet associations to 12, and the symbolic agent was able to learn all of them, while the actor-critic learned up to 2 pairs. Interestingly, the size of the reservoir and the type of the learning rule affected the number of novel PAs that could be learned in one shot. Still, the fully neural agent's performance is comparable to the rat's performance in SfN's task, indicating that a similar computation could be possible in the rat's brain. To conclude, both Steele and Morris as well as SfN's multiple pet association task can be solved by our biologically plausible agent that has a coordinate learning system and an episodic memory system that stores Q target associations. Our work expands on the episodic memory system such that the reservoir can be trained by Hebbian plasticity to store and recall Q-associated target information after a single trial of learning. However, in our current agents, the rule of associating Qs to target is handcrafted, and we have yet to formulate a schema learning model. Lastly, our current agents only move by direct heading and are unable to navigate past obstacles, unlike rodents. So with that, I would like to thank you for your time and hope we can connect through these platforms for further discussions or collaboration. The preprint for this paper is available on arXiv, and I would like to acknowledge the following grants that have supported this work. Thank you.